Okay, this class is Engineering 102, Statics. Static means stationary, and that means, of course, not in motion. In this particular class, so our structures are at rest and nothing is moving. Now the next class you have is dynamics, which dynamic means moving, and that dynamics is the study of moving bodies. So in this class, everything's not moving, stationary. The next class that you have, you'll start looking at things that are in motion. And the first topic in this class is beams. The second topic is trusses. So a truss being, something that looks like this. This is a truss, sort of looks like a bridge. And that's one example of a truss. Many examples of trusses. But those are the first two topics. And basically you need to understand these two topics very well and be able to do the problems assigned. It's, I want you to work very hard at these first two topics. Why? Because if you do this, you'll find the rest of the course very easy, very straightforward. So the main thing is, I really want you to focus on these first two topics, get them down, and you will find the rest of this course very easy. If you don't understand the first two topics, then you're going to be lost. So I'm just going to tell you that right up front. So, work very hard on these topics. Now, let me say one other thing. The way that I'm working this is, in this series of videos, is to integrate the homework directly into these videos. So you don't have to go to other sources. You just need to do these videos. So this is and work all the problems. Pause the video to work the problems. Work them through. Then the answers will be given to you and described. And if you don't get them, rework them until you get the problems. In other words, don't go past a problem that you don't understand. Keep working the problems until you get it. And it's really important that you don't say, okay, I understand it, without doing the problem. You have to do the problems. That's the only way that you're really going to understand it. So please don't just look at a problem that is given as a homework problem, what I call a homework problem, and then look at the solution and say, I got it, and go to the next one. You're not going to learn it that way. You actually have to work the homework problems yourself. Okay. So the first topic is beams. And a beam, I'm going to do a little example of how to solve a problem to find the reactions. Now, what is a reaction? The reaction is the force at a support. So here's a beam right here, and on it I have a 10 kip load and I have a 20 kip load. Well, what is a kip? A kip is 1,000 pounds. So K is a kip. We call it a kip, which is short for kilopound, which is 1,000 pounds. So in other words, 20 kips is 20,000 pounds. But we're going to use the word kip. It's standard. Now, if we look at this beam, how is it supported? I have a roller here and a pin. So a roller resists only vertical movement. That's what that represents. So in other words, if something is on a roller by itself, in other words, if I had a beam here, and let's just say I had two rollers like that, then I could come and I could push this beam, and this beam would roll along. Well, again, that's not what we're studying here. We're studying statics. And so we don't want anything moving. So we have the other support is a hinge, looks like that with a little dot. And that is what prevents this beam from moving if I were to put on a horizontal force. Now, just as a little aside here, this roller. This is just both of these obviously are just little schematics of what is actually used in such a case. What we're going to say, this roller can actually resist both up and down motion. So, if I were going to draw a roller a little bit more accurately, it would have an above and below roller, so that the beam cannot move up or down. But nobody ever does that. The way that a roller is drawn is a schematic is like this, but you have to know that both upward and downward motion is resisted by a roller. Okay, so let's take a look at this beam. And what we are going to do is to create a free body diagram. One of the things that I always warn people about is don't think that you've learned this well from physics or whatever previous classes you have had, because what I have found is almost everyone they've been taught it badly. Okay, so what I want you to do is do things my way here, and this is not my way, it's the way that is well established as the correct way to do it. So I'll call it my way, but it's the correct way that is well established, and I want you to basically forget what you've learned, except what a vector is. As long as you know what a vector is, you'll get through this class very easily. You can forget what you learned in physics. I usually start out with that. Forget your physics, because most likely you have developed very bad habits from your physics class. You may have been able to get the correct answer in some simple problems, but as we go to more complicated problems, you're going to find that your method, that whatever it is you learned in physics generally breaks down. So I want you to use my method. Like I say, it's not my method, but I call it my method. I want you to follow everything that I'm doing, forget what you've learned in the past, and you will get through this very well. If you develop, what's going to happen is that if you try to do it your way or the way somebody else taught it, and that is almost certainly non-standard, you're going to get into big trouble in a couple weeks. So do the problems the way that I show them here in the videos. What we're going to do is we're going to create a free body diagram, which I'm going to abbreviate FBD, free body diagram. And this is central to everything we do in this class, pretty much. And so you need to be able to draw this free body diagram at both the beginning of the problem and the end of the problem. So there's going to be an initial free body diagram, there's going to be a final free body diagram. How do we draw a free body diagram? Well, it's quite straightforward. I use a dashed line, dashed circle. It's got to be a complete loop. And it's not a circle, obviously, but you have to create a complete loop all the way around your structure, and you need to free it up. So the free body diagram means I'm going to free up this body being the beam. Now, when you do that, you are going to find you're going to make some what we call cuts. These are imaginary cuts to free up the body. And in finding the reactions, we make cuts at the locations of the support. So again, the reactions are the forces at the support. So in order to get the forces at the supports, we have to make cuts, imaginary cuts at the supports. And then everywhere we make a cut, we put a force or forces. So this is my dashed circle or dashed loop. And if I look at that, well, I'm making cuts through air. And this is all, in other words, if you look, we call cuts. I'm making a cut through air, cut through air, cut through air, air. Oops, I'm making a cut through the support, cut through the support, cut through air the rest of the time. So I don't put anything when I cut through air. Interestingly enough, when we get later on in this class, we will make cuts through water. When we make cuts through water, we will put a force. But when we make a cut through air, we don't put any force. So what you don't want to do, so this is not going to solve our problem, to come in here and make cuts underneath the supports. That's not going to get us the forces and the supports. So you don't want to, you must make a cut at the support to get the reactions. So what we do then is we have to, so the steps to drawing a correct free body diagram is to draw exactly what is contained in the dashed circle. So exactly. So you have to develop good habits here. So this is why I'm starting from this stuff that seems like it's very, very basic, and you might think, you think I'm going into too much detail here, but we need to develop very good habits right at the beginning of this class. And you need to forget, like I say, you need to forget the way you did this in the past, and you have to use this approach. So, as I say, that once we draw our dashed circle, so we draw our dashed circle, and then, so I guess in a way, so before this is first we draw the dashed circle. Of course, again, it's a circle. A loop, it must close. It must close. Draw the dashed circle. That's the first thing we do. And then what we do is we draw exactly what's in that circle. And everywhere we made a cut, we put a force or forces. And at a roller, when we cut through a roller, we put a vertical force with a letter next to it. Okay? And at a hinge cut, I put a vertical force and a horizontal force. And again, with letters next to them. Why? Letters meaning they're unknowns and we're going to solve for them. So in other words, here's my dashed loop or dashed circle, closed. It also includes the loads. We don't want to, in other words, I can't do this. I can't come in here and draw my dashed circle like that and get rid of that load. No, we've got to include the loads. So I can't come in here like that and try to get rid of the loads. I have to include the loads. So it's got to be up around here like this. And then what do we get? Well, we get something that you've probably seen at least a little bit, is here's my beam. So I draw exactly this. I can do it cut and paste. So a copy and paste. So if I do that, I'm just going to use the copy and paste tool here. What happens? I'm going to follow my dashed circle, and I'm going to come in here like that, and then I'm going to say copy, and then paste. Well, what do I end up with? I end up with what I'm supposed to end up with. And in other words, I have exactly what's in this dashed circle. Oops. What's in this dashed circle. And that's what I want. Now, where did I make those cuts? Well, I made a cut there, and I made a cut there. So I made a cut there, and I made a cut there. So what do I have to do? Then I have to put a force or forces where I made the cut. I made a cut at a roller, so I put in a vertical force. Like that. And then I put I'm going to call it A, or it's at A, point A, so I call it AY. And then I made a cut at a hinge, so I have a vertical force and a horizontal force. So where the hinge is, right here, I have both a horizontal and a vertical, and it's at B, so I call it BY, BX. And that is my initial free body diagram. So that is what is represented here. So this is our initial free body diagram. Now, we have unknowns here in this. So we're going to use it. Now we have to, the rest of the problem is looking at this free body diagram and being true to this diagram. And that is key. You've drawn it. Now you have to be, now everything you do from this point is you use it as it is drawn. You can't change it. You got to follow exactly what's in that drawing. And if we notice, we have unknowns. That's unknown. So any letter, so if I have a letter next to an arrow, it's an unknown. If I have a number next to an arrow, it's known. So I know that this, next to an arrow, it's a vector. This is 20 kips. This is 10 kips. So I know those. They're not unknowns. These are unknowns because I put a letter next to it. BY, BX, and AY. Those are my unknowns. And that I have 3 unknowns. Now, the equilibrium equations are, I have 3 equations that I can use. I can use that the sum of the forces in the x direction equals 0, the sum of the forces in the y direction equals 0, and the sum of the moments equals 0. Now in physics, you may have called moments torques, but in engineering, we use torque for twisting. We use moment for a force times distance sort of thing that is not about twisting. So we're not talking about twisting this beam. And so we'll see it. So you'll see how we're going to use the sum of the moments. So these are the equilibrium equations in statics. Is the sum of the forces in the x and y direction are 0, and the sum of the moments are 0. So that means we have 3 equations. So we have 3 equations, 3 unknowns. We're going to be able to solve this. Now, what we're going to find is that we're going to be able to use these. We only have 3 equations, but we're going to be able to use these equations in different ways, but only 3 of them to get these 3 unknowns. So now notice, the sum of the forces are 0. For instance, why are the sum of the forces 0? Because something is not moving. Now we have to pay attention to signs such that, up and down, we're going to call up positive, down negative. So another way to look at it is the sum of the forces going up equal to the sum of the forces going down. But if we assign positive and negative signs to them, then that means the sum of the forces is 0. So same thing, right and left. So the sum of the forces going to the right equal the sum of the forces going to the left. Now, the way that we interpret that is that we'll say that the forces going right are positive, the forces going left are negative, and since we're assigning signs to those, we are going to find that the sum of the forces is 0. And similarly, we're going to have clockwise and counterclockwise for the moments, and that's going to mean that the moments clockwise are going to be equal to the moments counterclockwise. We're going to take clockwise being positive, counterclockwise being negative. In other words, that the body doesn't rotate. The body is not rotating. It's not sliding to the right, not sliding to the left, it's not sliding up, it's not sliding down, it's also not rotating. So that's what the moments tell us. So when we have 3 unknowns, 3 equations, we can solve it. So that's how we're going to solve our problems. Now, it's very important, and that is the free body diagram. This free body diagram is very straightforward, but you need to develop good habits because eventually we're going to have more complicated free body diagrams. And you need to do these simple ones right, so that when they get to be more complicated, you'll get those right also. So you need to know how to draw a free body diagram. We're going to spend many weeks learning how to draw these correctly and analyzing them. And to solve problems in this class, you must be able to draw a proper free body diagram and focus on learning how to do that. Now, after a while, it gets to be very straightforward. So it's not difficult, but you have to pay attention. Okay, so in this problem, this is our initial free body diagram right here. And what we're going to do is understand what this is, and we're interested in, we have to pay attention to the line of action of forces. So this is an example. For instance, if I have a force, not on this free body diagram, Cx, and that's there, well, what is the line of action of the force? It goes all the way like that. There's a line of action. It's I have to pay, I'm going to have, basically it's just a long line that goes straight through the force. If I have a Cy, what's the line of action of that force? There it is. And it's, it goes all the way down there. It goes along, it's a long distance. It's a line. So you need to have an understanding of the line of actions of these forces. When it comes to moment, we're going to keep it pretty simple. You're going to find it's pretty straightforward. It's a force times distance thing, but we have to pay very close attention to what that distance is. It's the force times the perpendicular distance. Okay, what perpendicular distance is that? It's from the line of action of the force to the point about which the moment is being taken. So moments are always about a point. And we need to know this. So we need to keep this in mind. We'll go over it many, many, many times. But it's the distance. Again, the easiest thing is the force. The hard part is the perpendicular distance from the line of action of the force to the point about which the moment is being taken. So the hard part is the distance, and we got to focus on that. People miss that. And the other part is that we have to recognize that the moment is always taken about a point. So what we're going to do with this problem is that we are going to take moments about point A. So point A is right there. And we're going to take the sum of the moments about point A, and we are going to set, and this is what I want you to do for the rest of this course, for all the entire time you're taking this course, we're going to take, for this moment equation, we're going to take clockwise being positive. And so I'm always going to write this down for this equation, that clockwise is positive. So I want us all on the same page. I don't want us to do something else. I want you to always take the clockwise as being positive. So I'm taking moments about this point, so it's a force times distance thing. And in this particular case, it's pretty straightforward what the distance is. And so we're applying this equilibrium equation, the sum of the moments about A equals 0. And we're taking clockwise being positive. Well, what do I mean by clockwise being positive? Well, this A, since I'm taking moments about point A, that's the center of my clock. So when I look at my forces, for instance, this force here, well, we look at the arm of the clock or the hand of the clock. Here it is. There's the arm of the clock, or the hand of the clock is there. This is the center of the clock. And what happens? I'm going to knock the hand, that force knocks it like that, which is counterclockwise. Hope you can see that. You can see that this is counterclockwise. This is counterclockwise. We have set clockwise as being positive. So this becomes, when we write down our equation, and this is the way you need to write it down, is negative 10 times its distance 5. So 10 is there, the 5 is there, and the negative sign is because it is counterclockwise. We go to the next force. The next force is 20 kips. Well, I'm still taking moments about A. There's the center of my clock, and now the hand of the clock is over here. It goes to the force, and now what happens? It's going to knock that hand clockwise. So that's going to be positive, because clockwise is positive in our equation. So it's going to be plus 20 times the distance 6. So force times distance, very easy. What people miss is the signs. So you have to pay attention. You have to know that I'm taking moments about A. This is very important. You cannot forget in doing this step what point you're taking your moments about. You have to focus on that. And so that you get these signs right. Like I say, the force times distance is easy. 10 times 5, 20 times 6. Everybody gets that. What they miss is the sign. So this is a negative sign because it's counterclockwise. It's a positive sign because it's clockwise. So then I come over to by, and again, I'm taking moments about A. There's my hand of my clock. The force is pointing upward. We got to pay attention to the way that we had to look at my picture. It says it's going upward. What does that cause? That causes a counterclockwise. So that means it's negative. So I have by, and now the distance is 10. And so I have by times 10, but because it's counterclockwise, it's negative. So I have to be true to this picture. I just want you to recognize you drew the picture in the sense that you drew that going up, and you drew that going up, and that to the right. That's okay. We're going to find, you don't have to think about that. Once you've done it, you've done it. And now we have to follow this picture, forget everything else, to come up with these first 3 terms. Now, what about the rest of the terms? Well, let's look at it. AY, for instance, well, it's going to be AY times 0. There's no positive, negative, or anything because it's going straight through the point. So, I can throw it out. Why is it 0? Because the distance is 0. The force is AY, the distance is 0. Now, the one that, this BX, well, what does that mean? Well, what's the line of action of BX? Well, the line of action of BX goes through point A. So the line of action to the point, well, the line of action goes right through my point, so it's 0. So I have a BX, but it's 0. The distance, so I can get rid of that. I can get rid of that term also. So eventually we're going to see that these forces go straight through our points and just ignore them. So we get rid of these. I now solve this for by, and I get by is equal to 7 kips. So you can all solve this type of equation. So okay, so I get by equals 7 kips. Now, what I want you to do is I want you to use the moment equation again. So in other words, I know that you may have been taught in other classes that, now you're going to use the force equation, but no, I don't want you to do that. I want you to use the moment equation twice, so I require that. If you don't do this on the exams, I take points off. So you need to do the moment equation twice. Now why? I'll show you later. But let's do it. So now I'm going to take the sum of the moments about B. So I'm going to take moments about B. So that's my point. And again, it's one way to do this is just to write down force times distance, then worry about the sign. So let's do that. So I'm going to write, I've got 10 times 15. 10 times 15. So again, I'm taking moments about point B. I have AY times 10. AY times 10. So force times distance, everybody gets that. I've got 20 times 4. 20 times 4. And then, I can do BX goes through the point, so it's BX times 0, and BY goes through the point, so it's BY times 0. Again, because it's 0, I can just throw those out. But I now have, this is my equation, it's equal to 0, and I can solve for AY, and I get AY is 23 kips. Now you can use the sum of the forces in the x direction equals 0. Well, what do I have here? If I look at this, I only have one force in the x direction, it's bx, and so I get bx equals 0. So I only have one of them. Okay, so my unknowns, by is 7 kips, ay is 23 kips. Now what do I do? I'm going to draw the final free body diagram. So my initial free body diagram, remember, looks like this. Now what I'm going to do is I'm just going to take the numbers that I solved for these. Ay is 23 kips. I simply cross out the ay. So I cross that out, I write 23 kips. The by is 7 kips. I cross out the by is 7 kips. I cross out the by, I write 7 kips. Bx is 0. I cross that off as 0. So I don't need to show an arrow there. And so in other words, again, you got to follow this method very carefully here. So follow these steps. This becomes 23 kips. This becomes 7 kips. That is gone because it's 0. And I show my final free body diagram as this, which has the 23 kips here, the 7 kips here. And then we want to check our result. How do I check my result? Well, the upward forces must be equal to the downward forces. And so if I look at this, what do I have? I have 7 plus 23, that's 30 going up. And I have 10 and 20, that's 30 going down. So up equals down. The up forces equal to down forces. So that's my check, and that's why we use the moment diagram twice. 23 plus 7 is 30 going up, 10 plus 20 is 30 going down, up equals down. What happens if they're not equal? I got to start over. You made a mistake someplace. If up does not equal down, you made a mistake. So you must check your work at the end of this. Again, if you don't check it, I take points off. So you have to use the moment equation twice. You then have to check your work. And it's not a guarantee. In other words, if up equals down, it's not a guarantee, but it increases your likelihood of being correct. So not a guarantee, but put it this way. If your up forces do not equal your down forces, you're guaranteed to be wrong. There's something wrong. So, okay, so this is your final answer right here, and this is what you're going to be graded on. Right there. So focus on creating. You've got to be able to create this final free body diagram correctly. So, all right, I'm going to stop there and then we'll